Winding down to the end of the semester. Oh shoot, here we go again. What chapter are we on? I think this is chapter 29 that we're going to start to talk about. I'm not going to do an introduction to chapter 29 because what I'm going to do right now is motivate chapter 9 and really let you know that you already know what's in chapter 29. So we're going to set up a problem like this. Let's just say this is a railroad track. So let's say it's a railroad track, and let's say here is a metal bar. Actually, I'm going to make this metal bar only as wide as these railroad tracks. So ignore these parts out here. So here's a metal bar, and let's just say that it's moving with some velocity v. It's moving with some velocity v. And it is in a region of uniform magnetic field. So this is a magnetic field that fills all the inside of this railroad track. So what do we know? Well, we know that there's going to be a force on the charges in that metal bar. It is a metal bar, so we know those charges are going to move. But yeah, actually it's not even really that important right now. So what is this? The force is just QV cross B. So let's go ahead. I'm going to define this like this. Once again, this might be backwards for you guys, but let's see. I'm going to try to do this so it's forward for you guys. So we'll see. X, Y, Z. That might be looking backwards for you guys. I don't know. I apologize. Okay, so from my perspective, what this is, excuse me, V and B are normal to one another. Okay, I'm going to try to do it your way. So V and B are normal to each other. So this B for you guys, it looks like this B is in the minus Z direction. So B minus B0 Z hat, if I have that right. Okay, and the V is what? V is V is in the minus V0 X hat direction. Okay, so we have a velocity of this thing moving this way through a region of uniform magnetic field. And the force is just given by this. Well, we can just look at this and say, what is V cross B? Right-hand rule will let us know V cross B, and that force is going to be, in the minus Y hat direction. And then the question is, what is that force? Well, does sine theta ever change? No. Does V ever change? No. Does B ever change? No. Does Q ever change? No. So this is just Q, V, B. And that's our force. So now the question is, and this is in the Y hat direction. Now the question is, what happens, what is the work done by this force? And the work is just defined as F dot dl. I'm going to slide this over this way just a little, just to make sure that that's visible. I think it is, but just to make sure. Okay, F dot dl. Well, what's the dl over which the force is operating? It's this right here. So normally we would do this integral F dot dl, but does this force change as a function of y? No, it does not. So we have some length L, or distance between these railroad tracks, and so this is just equal to F times L, and that equals minus Q V B F. Okay, and why the reason this is just now a scalar, this is the work that's done, the energy that is added to the system. Y and the dl is also a dy, so cosine theta for this, f dl cosine theta. Cosine theta also does not change, which is why we're able to take everything on the integral. So cosine theta doesn't change, and not only does not change, but it's equal to 1, so we can ignore it. Okay, so this is it. This is the work done on the system. Well, what is the work done on the system in terms of things that you've already known? Well, if you have a system where work is being done, then that means you have a potential difference. So what is that potential difference? It's just defined as Q times V. And what is, and so this is equal to the work, and meanwhile, minus QVBL, I believe, let me make sure, I think we can ignore this minus sign because DL is this way, DL is vertical, the force is in the minus y hat direction, so this cosine theta is actually equal to -1 and not 1. So that means we're gonna change this to a +1. So this is a plus. Sorry about that. Okay, so now we're just can we figure out what this V is? We just divide by Q, and so we have a potential difference of VBL. What does that mean? What that means is between this point right here and this point right here, there is an electric potential. And that electric potential is introduced by the magnetic field, by the moving charges through a magnetic field. Okay, anything new in there? No, nothing new in there. You guys know all of that stuff. But now we're going to add just a little, well, we're not going to add anything. We're just going to think of it in a different way. So let's erase just about everything. So I'm going to write up in this corner that V equals V0 B0L. All right. So now let's look at something else. Let's look at this a little bit differently. Let's say, what if we were to take the same system here, but now put a little line here and a little line here. So these are railroad tracks, and remember, those are metal, they're conductors. And let's add some conductors here too. And what we want to know is we want to know what's the potential difference between these 2 points. Well, once again, there's nothing new here. You guys will recall when we first looked at circuits, anytime there is only a conductor somewhere, then the potential difference, or the potential of that location, is identical, or of those locations. Meaning, if there is a potential here, that same potential is all the way up to here. And if there's a potential here, that same potential is all the way to here. Okay, so what is that? That potential difference is this right here. It's the V0 B0L. So now let's think about this in a slightly different way. Remember, this is a region of uniform magnetic field. You will recall we talked about the electric field flux, the electric flux through a surface. Now we're going to talk about the magnetic flux through a surface. The magnetic flux through a surface is the same as it was for electric. It's just B dot dA, an integral over that surface, whatever that surface happens to be. Well, let's see what this is for this setup. Let's call this L, big L, from here to here. And we already know this. So B, you will recall once again, dA is perpendicular to the surface. So B and dA are in the same direction. So, and B for our problem is uniform, so we can pull it out of this integral. So we just have B. So really all we have is an integral of dA, but we can just look at this and see what dA is. It is L times L. So this is equal to B, big L, little l. But what is L as a function of time? Well, the L starts out at some L0, but what happens? It gets smaller by a distance V0t. Everybody see that? Because this rail, this wire, whatever we want to call this, is moving in this direction, this area is decreasing. So, so as that area is decreasing, we have, this is the amount that this length is decreasing. This other length, the width, is not decreasing, and B is constant. So that is our magnetic field flux. And I'm going to use the same notation we used before, except there's a B here instead of an E. Okay, so now let's ask this question. Let's ask the question, what is the change in this flux with respect to time? What is the time derivative of this magnetic flux? Well, when we look at it over here, there's only one term that corresponds to time, and that is this minus V0 LB. Okay, so look at that, and we say, this minus V0 LB, I think I've seen that somewhere before. And we look right over here at the computation we made earlier, and we have a plus V0 B0 L. And so we can just look at those two things by inspection, and we can say, you know what? The voltage here is equal to the negative of the time derivative of the magnetic flux through this area. So the voltage introduced between these 2 points is equal to the time derivative of the magnetic flux, the negative of the time derivative of the magnetic flux over this same area. So the reason we like this way of expressing this, and there are other ways of deriving this, this is just to convince you that it's reasonable. Well, for this particular problem, this was pretty easy to calculate what the Lorentz force on these charges was. However, there are many other geometries where that's not quite as simple. But this, it turns out, is still true. That there is a potential difference. I'm sorry. I need to make this the general statement. Here it is. There's a general statement. Okay, so the general statement that there is a potential difference which is created by a change in magnetic flux. Ooh, look how good that red pen is. Good thing I saved it. All right. So this general statement, it turns out, is true all the time. And it is true everywhere, meaning if they're, well, I don't want to get more complicated. So we'll just say there is a potential difference that is introduced by a changing magnetic flux. And that is pretty much the idea that I want to take out of chapter 29. And that's pretty much it. I think there might be a little supplemental one. I've got to remind myself what's in there, but that's pretty close to chapter 29.